All right, so thank you for having me here. This title requires a little explanation. By Calabi-Yau factory, I don't mean the uncountably many top research centers and institutes that Professor Yau has created all over the world. Rather, I would like to tell you about a research project that I have been doing in automating the generation of Calabi-Yau manifolds. Okay? This is a research program that I've been developing with my graduate students, Jackie Ip, along with Charles Arnold and Francois Chaton at Meta. Now you can see for the company's logo why I chose them for a partnership. Our first paper appeared on the archive last week, and we have several planned projects in the near future. So the vastness of the string landscape presents a serious computational challenge. The immensity of the landscape, as you know very well, stems from the multitude of choices of internal space on which string theory can be compactified. Even if you restrict yourself to a particular internal space, there are additional discrete choices, such as quantized fluxes, brane or bundle configurations that further enlarge the space of solutions. Yet, the number of string vector with bounded compactification volume is conjectured to be finite. This finiteness is an important assumption for statistical arguments in the landscape. It is also argued to be a universal property of quantum gravity. However, the actual scope of the landscape remains rather blurry. We don't have an agreed-upon estimate on the precise size of the landscape, not to mention an exact count of the number of solutions. Exact counts of string vector are known only in very tiny corners. For instance, even for an extremely simple toroidal orientable, you can count the number of solutions. There are already over 34 billions of distinct intersecting brane configurations that you can find. Now, to make further progress, a natural next step is to data mine the space of Calabi-Yau manifolds. Yau famously conjectured that in each dimension, there are only finitely many topological types of Calabi-Yau manifolds. Calabi-Yau threefolds are of particular interest because they yield four-dimensional vacuum configurations of string theory that could accommodate, in principle, realistic particle physics coupled to gravity. Now, if you generalize the discussions to F theory, you could replace the word Calabi-Yau threefold to Calabi-Yau fourfold that are elliptically fibered. Now, while Calabi-Yau threefolds are neither fully classified or even known to be finite in number, those that can be realized as hypersurfaces in toric varieties are, at least in principle, amenable to combinatorial enumeration. So there is a well-defined and simple prescription for constructing a smooth Calabi-Yau manifold by starting with a four-dimensional reflexive polytope. Okay? So a reflexive polytope is a polytope whose dual is also a lattice polytope. Through a specific type of triangulations that I would review shortly, one can obtain a toric variety within which lives the Calabi-Yau space. It serves as an ambient space, and the toric variety serves as the ambient space for the Calabi-Yau hypersurface. Up to lattice automorphism, the number of reflexive polytopes in any given dimension is finite. For example, there are only 16 distinct reflexive polytopes in 2 dimensions, all illustrated here. But the combinatorial complexity grows rapidly with dimensions. There are over 473 millions of 4-dimensional reflexive polytopes. All of them have been enumerated by Krause and Skake about 25 years ago. I don't remember the exact number, but it grows exponentially with the dimension, so it grows very rapid. 4,300, very good. We have an accountant here, so. But the truly formidable challenge lies not in the polytopes themselves, but in the triangulations. So triangulations that yield smooth Calabi-Yau manifolds are known as fine regular star triangulations. So fine here means that every lattice point of the polytopes arises as a vertex of some simplex in the triangulations. So this condition ensures that the resulting toric variety has only mild singularities, and this allows the corresponding Calabi-Yau hypersurfaces to be smooth. So regular means that the triangulations arises from projecting the lower faces of the convex hull of a lifted point sets in one higher dimensions. So this conditions ensures that the toric variety is projective and therefore emits a Kähler structure. And finally, star means that all the full dimensional simplices have the origin as a vertex. So this allows us to define cones forming a complete fan and ensuring, therefore, the compactness of the toric variety and the Calabi-Yau hypersurfaces defined with it. Now, this procedure is very standard and it's very simple to define, but enumerating all FRSTs is computationally infeasible because the number of them grows exponentially with the number of lattice points, which I will loosely refer to as the polytope size. So I would interchangeably say the polytope size and the number of vertices of the polytope, and you know what I mean by that. Okay, what makes the enumeration problem even more challenging is that different FRSTs can yield topologically equivalent Calabi-Yau threefolds. So therefore, enumeration of distinct Calabi-Yau, even in this very restricted set, is computationally infeasible. Even though an upper bound has been found, it's of the order of 10 to the hundreds. Now, in recent years, there have been excellent publicly accessible software packages that have been developed to make some of these computations involved more streamlined. For example, one of these great tools is known as CY tools, developed by the Cornell Group. Despite the tremendous speed up provided by these publicly accessible packages, you can do the calculation and estimate how long would it take to enumerate 10 to the hundreds of these solutions. It would take longer than the age of the universe to even uncover a sizable fraction of this part of the landscape. Okay. So if you felt uneasy about the estimate that Hiroshi made about the time scale for constructing a realistic model of quantum gravity, you should be exponentially terrified, right? The setup that we are discussing here. So clearly we need something other than a brute force enumeration. And the current state of affairs calls for a scalable, self-improving learning algorithm that could automate the generations of Calabi-Yau. Now, non-learning algorithms that I will also explain a little bit later on not scale very well with the polytope size. So you could try to enumerate these fine regular star triangulations by doing a lot of flips of a graph, but it scales terribly with the number of vertices. Okay. Moreover, previous computations offer very little advantage to further investigations that involve other polytopes. Okay. Now, there have been attempts to use machine learning to tackle this problem. Genetic algorithms and reinforcement learning have been used to perform targeted search. You can try to look for Calabi-Yau manifolds that give you certain desirable properties. For instance, if you want to get something close to the standard model or to get the axion couplings to be in the right range, you can try to design your machine learning model to optimize the search. But so far, this has not been done in expanding the search space. And it remains unclear whether the insights that you derive from triangulating one polytope would generalize to others. So, motivated by these limitations, we developed a transformer-based model to automate the generations of Calabi-Yau spaces. So we demonstrate success of our transformer in generating new Calabi-Yau manifolds as measured by several different metrics. So we show that our transformer trained on a set of relatively simple polytopes start to learn the rules and can successfully predict FRST for previously unseen and more complex polytopes. Another thing that we have shown is that the set of FRSTs that are generated by the transformer are representative of the full ensemble, okay? To the extent that we can check for smaller polytopes where we have a complete enumeration, we can compare the set of FRSTs that are generated by the transformer with the full distribution and see how much they approximate or fill up the distributions. So both are indications that the transformer is not just memorizing triangulations, but rather learning some meaningful structures of the data. So our results suggest that our transformer model that we creatively call CY transformer can be used to automate the generations of Calabi-Yau spaces in a self-improved manner. By that, I mean that you can train your transformer model on a relatively modest set of polytopes with a few triangulations, and the model is able to bootstrap its way up through successive iterations to generate increasingly more complex, to triangulate increasingly more complex polytopes. So, yeah. It's the name of the architecture. So it's used mostly in language processing. And so one of the key features of this machine learning architecture is something called the attention mechanism. And so it has been used widely in language-related set of problems. So we stick with the use of transformer. It's not the transformer in the context of physics, but it is a transformer in the context of machine learning. Now, this ability to generalize is what we find encouraging. And so it's a strong indication to us that the machine learning model is actually learning the underlying rules for constructing Calabi-Yau spaces. So let me introduce our transformer model. Okay. So a triangulation of a four-dimensional reflexive polytope can be represented by a sequence of four simplices. Okay. So you can represent a triangulation by a set, and all the sets that tells you what simplices are included. And the specific type of triangulations that give rise to a smooth Calabi-Yau that is known as fine regular star triangulation is a triangulation that satisfies a certain syntax. So the problems of generating FRST, therefore, naturally lends itself to a language modeling problem. Now, this is not the only idea we have tried. We have tried also a more geometrical approach using hypergraphs. So in a hypergraph, each node represents a lattice point of the polytope, and a hyperedge represents a candidate simplex. So if you were to train a hypergraph neural network, the hypergraph neural network will start to learn the rules, learns the probability for a certain hyperedge, indicating how likely that simplex is to be included in a particular, that simplex is to appear in an FRST. Okay. However, this offers very little advantage or insights into the structure of a specific FRST. Okay, so the analogy would be that you can learn the probability of certain words that appears in a sentence. For instance, the word "the" appears very frequently, so it has a high probability of appearing. It just tells you that the word "the" appears very frequently in a sentence. It doesn't tell you how these words are put together. In particular, in a given sentence, the word "the" may not even appear. So we would need to use a different ways of training a machine learning model in order to be able to extrapolate. So in contrast, transformers are designed for sequence modeling tasks, such as natural language processing. Right? This is the architecture that underlies ChatGPT and DeepSeek and all the language models that you enjoy. In the transformer model, the token-by-token generative framework enables the transformers to learn the structure of data in an autoregressive manner. So this is different from the hypergraph that I mentioned earlier. In this context, each token is a simplex. And so the machine learning model learns the probability for the next simplex conditioned on all the previously simplices that have been already generated. Okay? And the sequence of simplices that you generate through our transformer model, it would be a candidate FRST. And checking whether something is an FRST is a very easy thing to do. generating a solution would be much harder. Okay, so in a little bit more detail, the transformer model contains an encoder and a decoder. Okay. So the input of the encoder is a four-dimensional reflexive polytope, which can be represented by a set of vertices. So these are four-dimensional vertices because these are four-dimensional polytopes. And the encoder output would be a vector in some abstract embedding space. Okay? So taking the embedded encoder output as the input, the encoder generates autoregressively simplices to be included. So the output of the decoder would be a set of simplices that defines our candidate FRST. Now, the transformer model that we designed for this purpose has about 100 million learnable parameters. So for those who are in the business, you know that this is a very lightweight large language model. The language model that people are talking about now have learnable parameters of the order of 1,000 billion parameters. Okay. And so to get a sense of how this transformer model works, we started with a smaller set of training set. Our training set at the moment contains less than 10,000 polytopes. And for small polytopes, we can enumerate all the FRSTs. For larger polytopes, we sample a subset of them and put that into our training set. And it takes about a couple of days to run, to train this model on a few GPUs. This is certainly not something that is too intimidating. This is something that you can do it on a university level computing resource with your university level computing resources. And certainly we have not optimized the transformer model. We can do a lot better. We would expect that the performance to be a lot better if we spend time in optimizing the hyperparameters. Yes. So at the moment, we have not seen anybody trying to build a generative model for like this toric Calabi-Yau. The closest would be the hypergraph ideas that I mentioned earlier, but we haven't, because we tried it and it didn't quite work. So that's why we did not pursue that direction further. You can try to do reinforcement learning or genetic algorithms, but our sense is that you are not going to enlarge the search space significantly. It's just perturbations of what you have already seen. So, yeah, you could do that. But here, again, we are not claiming an optimal architecture. We are trying the simplest things that we can do in a reasonable amount of time. And if it shows promise, which I'm going to show in a moment, then it motivates you to actually do it on a more serious scale. So even the architecture, we have not thought a lot about how to improve it to make it optimal, but this is something for the future. This is certainly CY Transformer 1.0. Okay, so the input to the encoder is a four-dimensional reflexive polytopes. So a four-dimensional reflexive polytopes can be represented by an n-1 times 4 array of integer-valued coordinates of the vertices that define the polytopes. n-1 because we don't count the origin, which from the start requirement is guaranteed to be present anyways. And 4 because the polytopes are four-dimensional polytopes. Okay. So as an example, this would be a four-dimensional reflexive polytopes with 10 vertices. And what the encoder does is to learn how to convert the coordinates of these vertices into some abstract vector in an embedding space. So the decoder input is a sequence of 4 simplices. So you want to generate them one by one sequentially. And so each 4 simplex is your token. Okay. So now there is an ordering issue here because we order the simplices according to the order in which the vertices appear in the encoder input. So for example, this would be a simplex corresponds to a, this represents a 4 simplex with the following lattice points. So V0, V1, V2, V3, and then Similarly, this 99 means that this is a 4-simplex composed of a certain number of vertices. And so we order the simplices according to the order in which the vertices appear. Certainly, this is something that you would not expect to change anything, because if you were to build the vertices of a polytope, it's still the same polytopes. So if you were to train a machine learning model sufficiently, the model would learn the underlying permutation symmetries. But if we were to scale up the project in the future, we would have to think about employing a more permutation invariant architecture, such as a set transformer. So the vocabulary consists of the following tokens. So as many distinct 4 simplices you have, so n-1 choose 4, together with some special tokens for the start of sequence, end of sequence, and padding. Okay. So for example, this would be an example of a decoder input. Okay. It tells you the start of a sentence and what simplices are included in the triangulations. And then the number of padding is it's what defines the model. It's not going to be too relevant for our discussions. Now, one thing you may notice is that the vocabulary grows with the number of vertices. And in fact, it grows exponentially. And so this problem can be, in principle, mitigated by using multiple tokens to represent the same simplex. For instance, instead of using a token to represent one 4-simplex, you can use several tokens to represent 2 simplices, 3 simplices to build a 4 simplices from it. So that has the advantage of reducing the vocabulary size and still be able to train the model to learn the structure of how triangulations would give rise to smooth Calabi-Yau spaces. We have tried some of this. It doesn't deteriorate the performance too much. But at the moment, we are still using the 4 simplices to encode what triangulations we have. Okay, so later on, I will use a measure known as the height vector similarity to quantify the diversity of the FRST that are being generated. So for that, I would have to review for you something about the regular conditions. Okay? So a regular triangulation can be constructed by lifting the lattice points to one higher dimensions and then projected on the lower codimension 1 faces projecting on the lower codimensions of faces. And so this is an example. So you have a set of lattice points, you lift them, there's a certain height vector that tells you how high the points are lifted. When you project the lower codimensional subfaces, you get these triangulations. But not all projections results in triangulations. Sometimes you get projections that result in subdivisions that do not fully divide the polytopes into simplices. But this is something that is easy to check. The fine condition is extremely easy to check, and the star conditions can be met by simply lower the origins. Okay? So if the origin is not included in the triangulations, you lower the origin so that it's always in the lower codimension 1 surface. Okay, now for small polytopes, you can enumerate all the FRSTs by performing bistellar flips. So this is a pictorial way of doing this. And there are actually standard packages for doing this, known as TopCom. However, the number of FRSTs grows very rapidly with dimensions, and it quickly becomes invisible, even for moderately large polytopes. So we need a sampling algorithm rather than direct enumerations. Okay? So a triangulations that one can always construct for any polytope is known as the Delaunay triangulations, where the height vectors, the picture that I showed you earlier, there's a height vectors associated with each lattice point, where the height vectors is set by the norm of the position vectors of the lattice points themselves. And when you project the lifted points to one lower dimensions, you don't always end up getting a triangulations, but you can quickly fix the fineness condition as well as the star conditions, and to make sure that this is indeed an FRST. And using this Delaunay triangulation as a seed, you can generate additional fine regular star triangulations by sampling the height vectors from a Gaussian distributions. Okay, so this is the idea that has been put forth by the Cornell group. And this algorithm is very fast because it's a sampling from a Gaussian distribution, but the FRSTs that are generated are not very representative of the full ensemble. And you can combine this fast algorithm with some random flips to improve diversity. But the random flips are very expensive to do because the number of possible flips grow super exponentially with the number of vertices, whereas the number of FRST grows only exponentially. So you have to be very lucky to be able to get an FRST just by doing this random flips. Another way to assess how diverse are the FRST generated is whether the triangulations yield topologically distinct Calabi-Yau or not. So there is a Wall's theorem when applied to simply connected Calabi-Yau threefolds with torsion-free homology implies that the topological types are completely classified by the Hodge numbers, the triple intersection numbers, and the second Chern class. Okay? So this topological information is oftentimes known as the Wall data. Now, for toric constructions, the Hodge number depends only on the polytopes themselves, not on the triangulation. So it's very easy to compute. The triple intersection number and the second Chern class are specified by the restrictions of the triangulations to two faces of the polytopes. So therefore, a meaningful measure of representativeness of the FRSTs being generated is whether the model is able to generate non-two-phase equivalent Calabi-Yaus. Okay? So this is one of the things that we will use to compare different algorithms to see how diverse are the sets of Calabi-Yau that are being generated. Okay, so a moment of truth. So these are some plots that shows how well a transformer model is doing. So on the top, these are the FRST generation curves. It counts the number of FRSTs that are generated with the number of guesses that you made. So this here we are making 1,000 guesses. So different curves represent different things. The dotted line here counts all FRSTs that you generate, but then sometimes you overcount because they're not distinct. So the distinct FRSTs corresponds to the solid line. But then among the distinct FRSTs, some of them would give rise to the same Calabi-Yau. We only want to count the non-two-phase equivalent one. So this would be quantified by the third line here. So you see that the model is learning to predict FRST with the number of guesses that the model makes. And this generation curve is average over 200 test polytopes that we set aside. So these test polytopes have never been seen by the transformer model. So they are learning from the other polytopes that they triangulate to be able to generate new triangulations that give rise to Calabi-Yau spaces. You see that you can count the number of distinct non-two-phase equivalent one. You can generate a sizable fraction of them. Another way to present the results is to look at the generation rate, which is basically the slope of the curves on top. Okay? So a constant generation rate means that the model keeps on generating FRST at a reasonable rate. Here is close to 80%, but this counts all the FRSTs. So as you make more guesses, sometimes you make the same guess. So the actual merits should be about counting distinct FRST. So clearly the rate has to drop because the more guesses you make, the more likely you're running into previously generated solutions. And you can see that for polytopes that are smaller in size, number of vertices corresponds to 10, which is equivalent to Calabi-Yau with Hodge number equals to 5, 6, and 7, and so on. You see that the generation rate drops to 0. This does not mean that the model failed. It just means that the model has already successfully recovered most or all of the FRSTs for that polytope size. As you go to larger size polytopes, you find that the rate does not drop to 0, meaning that the model continues to learn, it continues to explore. Okay? And you can see that as you scale up the size of the polytopes, the performance maintains rather stable performance. The performance remains rather stable. Now we would like to, yes. So at the moment, we've gone up to h1 equals to 9, but we only show the results for 8 because for h1 equals to 9, we have not cross-checked enough. But h1 equals to 8 is already beyond the current record. I think the complete enumeration at the moment in the literature only goes up to h1 equals to 7. So later on, I will show you some performance when you go up in Hodge numbers. The transformer model is actually doing better for more complex polytopes. So yeah, so to answer your questions, this would be the set that has been completely enumerated in the literature. We have completely exhausted 8, and 9 is, we have already the results, but we didn't put all the results in the paper. Okay, now we would like to assess how representative are the FRST generated. And one natural measure of similarities of the FRSTs is a quantity that is known as the flip distance, which is the minimal number of flips you need to do in order to transfer one triangulation to another. So if two triangulations have a very short flip distance, that means they are very similar in some sense. So that was the first thing we want to try to compare. However, this would quickly become not doable because the number of possible flips, as I said, grows super exponentially with the number of vertices. So if you were to try to find the shortest path connecting two triangulations, that would be a very expensive, difficult calculations. So instead, we use the height vector similarity as a proxy for how broadly the model explores the space of STs. If the height vectors are very different, then in some sense they're different triangulations, and maybe they would tell you that there are different Calabi-Yaus. But there's a subtlety, of course. If you rescale all the height vectors by a constant, you're not going to get a new triangulations. So just comparing the height vectors means very little about how different the triangulations are. Moreover, two height vectors that differ by an affine function of the coordinates of the lattice points also give rise to the same triangulations. So in order to remove this ambiguity, we project the height vectors orthogonally to the affines of space, and then we compute the cosine similarities between the projected height vectors with that of the unique Delaunay triangulations. So the reference for us would be the Delaunay triangulations, the height vectors corresponding to that, and we measure how similar are the two set of height vectors by comparing the cosine similarities. And so that overall rescaling of the height vectors would not matter if you calculate the cosine similarities. Okay, so here's one way to represent what the transformer does. So I told you that there are 200 test polytopes. Okay? And here I randomly pick 16 of them. And just looking at the height vectors distributions, and by the way, this is corresponding to h11 equals to 8. And for these toric constructions, the Hodge numbers are related to the number of vertices. And in general, there are additional contributions coming from the number of lattice points within codimension 1 and codimension 2 phases. But for something that is known as favorable polytopes, they don't contribute. So I'm focusing on the favorable polytopes where you can drop this 2, which means that the difference between the Hodge number and the number of vertices is 5. However, the statement that we're making is independent of whether the polytopes are favorable or not. We are asking the questions about triangulating polytopes with n vertices. You can interpret the results the way you like it, but only when you want to connect it to Calabi-Yau, then you will need to make these extra assumptions. Okay, so looking at this height vector distributions, just by eyeballing, you see that the FRST generated by the transformer looks very close to the actual distributions. Okay. This distribution looks very strange, but that's because there are only very few triangulations for that particular polytope, so there's nothing buggy about it. But if you were to compare the distributions, they follow the shape of the actual distributions. Moreover, you see that the shape of the distributions is preserved as the transformer make more and more inference. So you could you could look at the distributions of the height vector as you account for 1/3 of all the FRSTs that you recover. 67% or 100%, the shape is preserved. It's basically a rescaling of the distributions. So that is an indication that the sampling is rather fair. Okay, so not all Calabi-Yaus are created equal. You could look at the performance for individual polytopes instead of averaging over the 200 test polytopes. Okay? So I picked two of these plots to show you the following points. You can see that there are 200 lines here because we have 200 test polytopes. Some test polytopes plateaus at a very low saturations. So here is one example. It plateaus at 40%. It never gets up beyond 40%. So this suggests that the corresponding Calabi-Yaus are harder to learn. There are a lot that you get to all of them. So there are the Calabi-Yaus that are easier to learn in some sense. We haven't looked inside the black box to see why these Calabi-Yaus are harder to learn than the other, but that's something that we could do in the future. Other than the ones that plateaus, there are some polytopes that have a very small growth rate, but it does not plateau. So this might be an indication that the corresponding polytopes are more complex, or the fact that there are many more FRST for that polytopes that we need to learn. Here we are counting the percentage of the FRST that are recovered, and if a lot more FRST that are hidden in these polytopes, that will take a lot more cases in order to recover all of them. Okay? So these are some data analysis that you could do after you run this experiment. Okay. Now you can compare this performance of CY transformer with the fast algorithm that I mentioned earlier. So you can compare them in terms of the percentage of the FRSTs that are generated. So since we have already completely enumerated all the FRST up to H11 equals to 8, I can show you all of these plots. Okay, so the coloring scheme is the transformers are blue and the fast algorithms are red. And you can see that for small polytopes, the fast algorithm significantly, does better, although the transformer is not doing so badly. Okay. So the fast algorithm recovers 100% of the FRST, whereas the transformer only get you up to 85% or so for small polytopes. So in other words, the transformer, so the fast sampler recover the FRST much more rapidly. By H11 equals to 7, the transformer catches up in performance. And by H11 equals to 8, the transformer significantly outperforms the fast algorithm. This, again, can be easily understood because when the space of FRST is tiny, the fast sampler can quickly, exhaustively enumerate everything, whereas the transformer is designed to focus on the more representative triangulations, and in the process may simply skip some of the more similar ones. Okay? So a message that you can draw from this experiment is that the fast sampler is a very efficient local scanner, whereas the transformer is a fair global explorer. Okay. You can also compare the height vector distributions generated by the transformer in comparison with the height vector distributions generated by the fast algorithm. And so again, if you look at the distributions just by eyeballing, you can tell that the transformer gives you a much more representative distributions closer to the actual ground truth than the fast algorithm would provide. Now you can quantify this. So here, if you just look at the distributions, you see that the fast algorithm generates for you something very skewed, whereas the transformer basically reproduces for you the full distributions. You can quantify how effective they are in exploring the full ensemble by computing, again, the cosine similarity of the height vector distributions with the ground truth. And if the cosine similarity has a score of close to 1, that means the two distributions are identical. So they never reproduce to you the identical distributions, but it's getting very close. The transformer generated FRSTs peaks near very close to 1 with a very low variance. Okay? So this tells us the following, that a transformer-based model gives you a fair global exploration of the space of triangulations and hence the corresponding level, whereas the fast algorithm gives you an effective local scanning of the triangulations that you can do for the polytopes. So the complementary strength suggests a powerful hybrid approach. You could use your transformer to generate seeds of FRSTs, and you can take that as a seed and sample using the fast algorithm locally, doing local explorations. So you get the best of both worlds. You have combinations of unbiased global coverage as well as high local efficiency. So again, can show you how well you do. This hybrid approach recovers more FRSTs with the same number of guesses than the transformer or the fast algorithms alone. Now, the population shape, which you can see, looks very close to the actual distributions. They basically is a clone of the actual distributions. The population shape is recovered with just 500 guesses. These 500 guesses were made from the transformer. And so this picture basically tells you that the unbiased sampling of the food ensemble is maintained using a combination of fast and transformer. And so this would be a rather low-cost, effective approach to generate as many triangulations and hence Calabi-Yau as you like. So a key advantage of a learning-based model is the prospects of self-improvement. You cannot do that with direct non-learning algorithms. Okay, so you could start by training a machine learning model with a very small number of polytopes with a limited number of triangulations. And so once the training loss plateaus, you can pause the training of the transformer and use the trained model to infer new FRSTs, candidate FRSTs. Once the FRSTs are validated, you can add back to the training set and repeat the process. Okay? So we have seen some clear sign of self-improvements. So here, if you were to start with a very small training set with 8,000 polytopes, with 5 FRSTs per polytope, you get a 25% gain by retraining on the FRSTs that were generated from the transformers. So you can imagine that you can repeat this process. At some point, it will plateau, but it does get you a lot more triangulations that were not obtained before. Okay, so how do we scale up the problem? So the lessons that we learned from CY transformer, I will summarize as follows. Machine learning models can generate unbiased samples, and there is a possibility to self-improve on these samples that you generate. And further techniques, such as priming, can enable reliable generalizations. So what is priming? Priming is basically training on a substantial set of training set, and you add a few more challenging examples. And the machine learning model, after seeing these few challenging examples, not the complete set, we're able to start to generalize. So the more challenging example here would be, suppose you were to train the machine learning model with up to 14 vertices, and you sprinkle a field with, say, 20 vertices, 50 vertices, and the model will start to draw the connections between smaller problem and harder problem. And to really realize these bootstrapping potentials, we need constantly evolving models and data set. So this is very different from what you would have done before the advances of machine learning. People talk about database and all that, Calabi-Yau database, but the database that we were talking about 10, 15 years ago were static database. I mean, you enumerate what you have, you put it into a common domain, people can try to do data mining the way that you want. But with machine learning, that means that you're not satisfied with just a static database. You want your database to be constantly updated, as well as the model that generates that. So if you start to go up in terms of the level of difficulty, the parameters that define your transformer model will also change. So this certainly cannot be done by a single person or a group of people, small group of people. We need a concerted effort. As an analogy, let's imagine that you have only one telescope for surveying all the galaxies in the universe. Sure, you can keep your telescope running for a very long time to collect more data in order to shrink the error bars. But it would be a lot better if you have many, many more telescopes, or even better, have many, many different types of telescopes. So we need a community-driven infrastructure for a large-scale problem like this. So this inspired us to launch what we call IC. It's an AI-enabled living Calabi-Yau repositories. Okay. For those who have seen people doing all kinds of fun but questionable things on a frozen lake in Wisconsin winter, you'll get an idea why we call this IC. So we are planning to have a full launch later this year. But at this point, for those who are interested, you can sign up for beta access. So we could share with you the codes that we have. You can run it on your local machine, generate as many Calabi-Yau as you desire, or maybe find some interesting mathematical relations that have not been discovered before. This is the QR code. Okay. Okay, so IC is not just a database. It's a communal platform for code sharing and data repositories. So not only can the users download the existing Calabi-Yau data, anyone who is interested in this problem can contribute to this repository by uploading the Calabi-Yau that they discovered, whether by machine learning or not. They can use their own model of machine learning. They can generate it by brute force. Once your generated Calabi-Yau have been validated, we could put that into the database. And this growing database feeds back to the training, enabling the generation of even more Calabi-Yaus. Okay? Now, this communal platform also supports targeted search. Suppose you are interested in looking through this database and find Calabi-Yau that has certain desirable properties, for instance, axial decay constants with a certain range. You would be able to do that by designing your callable functions and embed it into this framework. Okay, okay, so to summarize, the fundamental laws of physics are written in the language of mathematics. And the problem of generating Calabi-Yaus naturally lends itself to a language modeling problem. And so we have developed a transformer-based model that can be used to automate the generation of Calabi-Yaus. And our model shows it's potentially scalable, and it shows promise of continuous improvement through self-training and priming. And now with an effective new vacuum generator, you could ask the interesting physics questions as well as mathematical questions. You could ask what are the physical implications of this space of Calabi-Yau that you generated. You could also try to see from the many, many Calabi-Yaus that you generated whether there are new mathematical relations that were not known before. And so we are looking forward to tell you more about our progress in the next ICPS. But if you cannot wait, Madalena Leffers, myself, Harold Starker, and Mike Stillman are organizing a 5-week thematic program in Vienna where related topics will be discussed. So let me just stop here. Thank you.
Thank you very much for that nice talk. Any questions or comments?
Thanks. If you deploy your technology to the polytope with the largest number of points, what happens? Does it not work at all, or?
So this model success depends on the training set. So if you say you start all the way from 491, when it goes to 491, then you would have to generate at least a few and a sizable training set, which can be done with fast, maybe other algorithms that you come with. Once you build a sufficiently substantial training set, you can start to leapfrog from what you have and generate more. But the first step is to generate enough of the samples.
How many would you need?
Well, So I show you an example where each of these polytopes, I only have 5 FISD, I start to generate, and then if we repeat this process, we may be able to generate, iteratively more and more. But I don't have an answer unless we have really explored in any detail. So that process that I showed you, there are 5 polytopes that we use, 5 triangulations that we use for each polytope, and you start to generate like 25% more, and then if you were to build up further, you will be able to increase your training set.
Thanks. Any more questions?
Yeah. Yes. Certainly. Right. So we had this conversation earlier. I don't know how representative this is among the space of all Calabi-Yau, but for me, I would, for the moment, be happy if we have a way to data mine a sizable fraction of this. I mean, you can also ask the questions about F-theory, right? If you were to count the number of reflexive polytopes, we don't know the exact number of reflexive polytopes. And so they estimate that the Hodge number goes up to like 100,000. And so I think if we were able to do it for the KS database, we have a much better chance to be able to do it for the fourfold and perhaps non-toric constructions. That I don't know of a clear strategy for something that is non-toric, because here there's a very well-defined combinatorics problem. And machine learning is extremely good in solving combinatorically difficult problems. So that's why they're very good in playing chess. And for non-combinatorial problems, then we have to think harder what's the right machine learning model. That would be the second question, yeah, certainly. Yeah.
So just to clarify, just to compare with the other AI-based techniques, so you said this is you could reach H11 equals 8 database from this, and the others probably you said only up to H7.
So I think it's a matter of how much effort you put in.
Right.
So for the moment, what has been reported in the literature is up to H11 equals 7, I think.
They couldn't go to H1 equals 8, for example, because it took so long, or compared to yours, maybe?
Yeah, I think the problems scale terribly with the number of vertices, but although going from 7 to 8 is not so terrible that we can still do it. The hope here is it doesn't necessarily scale exponentially, because the models start to learn. Maybe it's better than exponential. Maybe we start to learn some recursive relations. It's possible, right? So the way they triangulate, you triangulate polytopes, maybe there are some recursive relations to sort of reduce the problem to smaller number of vertices. And if you were to be able to do that, then it's not going to be as bad as you originally estimated. But we do it just basically using the algorithms that we have. The transformer that can enumerate all the FISD up to H11 equals to 9 at the moment. So we didn't put the 9 in the paper because we wanted to be absolutely sure to report the results. But 8, we are absolutely certain what we show in the paper is the entire set.
But you think that the previous tricks, the complexity grows exponentially?
Yeah.
If you just rely on the previous trick, and here you have some hope, is that?
So I'm making 2 statements, right? So here for H11 up to 8 or 9, it's not terribly big that we can enumerate them. So in fact, that's how we validate our answer, right? So we use our methods to get a very fair distribution. In the end, how are we certain that we have the right answer? We use the fast algorithm to check. And so for small enough H11, you can enumerate that. Together with flips, you can still do it. And so we want to be absolutely certain for maybe up to H11 equals to 10. Once we have the full confidence that this is a very representative distribution, then we can scale up the problem. So there, I don't think we have anything to check against. And one thing which would be very interesting is, suppose you are able to with enough confidence that the distribution is very fair, then you may not even need to enumerate, because the generator is much more important than the database, right? So you can generate a Calabi-Yau on demand rather than trying to enumerate all of them. So you can see that in the distributions, at least our way to quantify the differences, using a small number of guesses give you a shape that looks the actual distribution. So then, you may not enumerate everything, but if you get to like 5% of everything, then the model is a very good generator of toric Calabi-Yau.
Any more questions? Not, let's thank our speaker again.
Thank you.